All right, today we're doing the first page of salmon colored notes dealing primarily with electromagnetic energy. All right, so energy in Earth's processes. Energy is the ability to do work, and we've looked at a bunch of different types of energy. Some of the types of energy we've looked at are kinetic energy and potential energy. So an example of that would be this golf ball right here. All right, so like right now, the golf ball is not moving, but it has a lot of potential to move if I take my hand away. So right here, it has a lot of potential, but no kinetic. Kinetic energy is the energy in motion. So right now, it's not moving, so it has zero kinetic, but it's got a lot of potential. I let go of the ball and let it fall. As it's falling, it's going faster and faster, so it's gaining kinetic, but it's running out of room to fall, so it's losing potential. That split second before it hits the ground is when it's going the fastest, and that's when it has the most kinetic, but it doesn't have any room left to fall, so it has the least amount of potential. Now it's bouncing back up. On the way up, initially it's going really fast, but then it's slowing down. It's going up, so it's gaining potential, but it's slowing down, so it's losing kinetic. Eventually it's going to reach a point where it stops, so it has zero kinetic and a lot of potential, and then it starts to fall back down again. All right. But that was only one example of kinetic and potential energy. Another examples you could use is this guy right here, all right, a rubber band gun, all right. So I take the rubber band and I load it in the rubber band gun like this, all right. Now, the rubber band's not moving right now, so it has zero kinetic energy, but it has a lot of potential to move if I pull the trigger, all right. And what happens, normally now I'd shoot a student with a rubber band, but I'll have to shoot towards the camera. What'll happen is as I pull the trigger, all that potential energy stored in the rubber band gets released and turns into kinetic energy, like that. So that's another example of kinetic and potential energy. Another example, just think of battery, all right? Now, the battery, it's not moving, it's not doing anything right now, so it doesn't have any kinetic energy to it, but it has a lot of potential energy in there. If I take that and I put this battery into a toy car, the car can move around. So the energy, potential energy that's in the battery would get converted to kinetic energy. All right. So those are just some examples. Another kind of energy, thermal energy, is basically heat. A key thing about heat energy is that heat energy always goes from the hot thing, the heat source, and it flows in the direction of the cold thing, the heat sink. So heat always travels from hot to cold. If something is dropping in temperature, it's not because it's gaining cold, it's because it's losing heat. There's no such thing as gaining cold. If I open up the window to this room, to the outside, and the temperature of this room decreases, it's not because I'm gaining cold, it's because I'm losing heat. So the hot thing is the heat source, and the energy travels to the cold thing, the heat sink. All right? And we'll do a few labs that deal with that in the near future. What we're primarily focusing on today, though, is electromagnetic energy. All right? Electromagnetic energy is energy that travels in waves from one place to another. Okay? So what a wave looks like, a wave can look something like this. All right? Now, there's a bunch of different types of electromagnetic energy: gamma rays, ultraviolet, infrared, microwaves. And what difference they have is they have different wavelengths to them. All right? So what a wavelength is the distance from the top of one wave to the top of another wave. Right? That's a wavelength. So if I had something that looked like so if I had something look like this, here the waves are very close together. This would have a short wavelength. Here the waves are a little bit farther apart. Here the waves are farther apart. So this would be the shortest wavelength. That would be the longest wavelength. All right. So wavelength is the distance from the top of one wave to the top of another wave. Now, this chart here, this is one that's in your reference tables. So I'm going to blow it up on the projector here so you can see it better. All right, so this chart is on page 14 of your reference tables. It's the electromagnetic spectrum, so it shows you all various types of electromagnetic energy. Most of these you've probably heard of, radio waves. I mean, that's how you get radio stations, is they broadcast radio waves. Microwaves, you have microwave ovens, that's what you cook with. Infrared energy is basically heat, like if you go by if you're to the side of a fire and you feel the heat coming off the fire, that's infrared energy. Visible light right there is what you can see. Ultraviolet radiation, that's the stuff that you have to put the suntan lotion on your skin to prevent skin cancer and sunburns and stuff like that. Because ultraviolet can kind of penetrate into your skin and could damage cells. X-rays, they could penetrate even further. X-rays, if you ever thought you may have broken your ankle or something like that, it might take you to a doctor and it might use X-rays to look what your bones look like. Because with X-rays, what happens is the X-rays can travel through the flesh, but they get stopped by the bone. So that's why you see an image of the bone. And then gamma rays pretty much shoot right through you. All right, so those are various types of electromagnetic energy. Now, a few things about them. Well, if you look at the chart, it says decreasing wavelength this way. So on this side of the chart is where all the waves are really close together. Increasing wavelength that way. So the farther you go that way, the farther apart the waves are. Now, visible light only makes up this little tiny portion of the electromagnetic spectrum. So what they did in this diagram, instead of trying to cram everything right there, they took this little part right there and they blew it up. So all this fits in that little section right there. Now, visible light, the stuff we can see, is broken up into a bunch of colors. And so you have various colors of the rainbow. Right? Now, the reason why we have different colors is because each color has a different wavelength. So since red is on that side of the chart, red is the color that has the longest wavelength, orange is a little bit shorter, yellow is a little bit shorter, and so forth, till violet is the shortest one yet. All right? So that's the portion that we can see. So this, all this right here fits in that one little section of the chart right there. All right. Next, another thing about this is when it says visible light, that's the portion of the electromagnetic spectrum that we can see. Other animals can see beyond that. All right. There's some types of snakes that see into the infrared. All right. So again, infrared is basically like the heat being given off by things. So like if it's at nighttime, they can see the heat being given off by things. So at nighttime, the snakes can see you, but you can't see the snakes. This is true for some snakes. Ultraviolet, there's some hummingbirds that can see into the ultraviolet. So when they look at flowers and stuff, they see like different things from what we see because they can see basically more colors than we can. But anyways, that's the electromagnetic spectrum. All right. So Some properties of the electromagnetic spectrum. Well, first off, all objects above absolute zero, which is minus 273 degrees Celsius or 0 degrees Kelvin, radiate some form of electromagnetic energy. Absolute zero is the coldest temperature you could possibly go down to. You can't get any colder than minus 273 degrees Celsius. Now, if you're wondering, if I got down to minus 273 degrees Celsius, why can't I go down to minus 274 degrees Celsius? Kind of has to do with what the definition of temperature is. By definition, what temperature is the average kinetic energy of molecules. All right. Now, molecules move. All right. When molecules are hot, they move a lot. When molecules are cold, they move less. All right. So what's happening? Let's say I got down to minus 270. All right, that's pretty cold. The molecules are moving very slowly. Minus 270, minus 272, or 271, minus 272, and then when I get to minus 273, the molecules stop moving. So if by definition what you're measuring with temperature is the movement of the molecules, and you reach a temperature when they stop moving, you can't get any lower than that because they can't not move less, all right? So minus 273 Celsius or 0 degrees Kelvin is the temperature when the molecules stop moving. That's why you can't get any lower temperature, because by definition, the temperature is you're measuring movement and it stopped moving at that temperature. But anyways, anything above that temperature is going to radiate some form of electromagnetic energy. Now, something like a light bulb gives off visible light. Something like this cabinet here, it doesn't look like it might be emitting anything, but it's giving off some type of heat. Right? Because if I were to bring this cabinet, which is about 20 degrees Celsius right now, or about 68 degrees Fahrenheit right now, if I were to take this and put it in a freezer, all right, this would be the warm thing, and this would radiate heat to the other things in the freezer. So anything above absolute zero gives off some form of electromagnetic energy. B, all electromagnetic energy travels at the same speed, the speed of light. All right. So you know it is a speed of light, but all these travel at the same speed. So gamma rays, X-rays, and so forth, they all travel at the same speed. 3 times 10 to the 8 meters per second. So that means it can go around the Earth several times in a second. That's how fast the speed of light is. And it's the fastest thing we know of. C, forms of electromagnetic radiation are distinguished by their wavelength. All right, so we basically pretty much talked about that already. So the reason why gamma rays are different than X-rays, are different from ultraviolet rays, again, it's because their wavelengths are different. The farther you go this way, the waves are closer together, the wave heights are closer together. The farther they go this way, the waves are spread farther apart. Now, what happens to electromagnetic energy when it hits a material? Right? Now, this is going to be true for all types of electromagnetic energy, but what we're most familiar with is visible light. So we use that as an example. All right. One thing that can happen is when electromagnetic energy hits a surface, it can hit the surface and bounce off of it. The word we use for that is reflect. And some materials reflect energy better than other materials. The best reflectors are things that are light colored and smooth, are the best reflectors. So like in this room right now, probably the best reflector is this whiteboard, because it's white in color and it's smooth. All right. Now the wall's white in color too, but it has a rougher texture to it. So this would be a better reflector than that would be right there. Snow is light and smooth. So like in the wintertime, even though the sun's lower in the sky on a sunny day in the winter, it's like super, super bright because the sunlight hits the snow, and then a lot of that sunlight just bounces back up. So you're almost like you're getting hit by the sunlight twice, once on the way down, once on the back up. Where in the summertime, when you got grass and trees and stuff like that, that's darker in color, so it's going to absorb more of it, and it's not going to reflect as much. Now, another thing that reflects energy very well are like metallic surfaces. A lot of metallic surfaces, like the back of a mirror is metallic. That's why mirrors reflect. And something that they use they use that property in emergency blankets. So sometimes you may see a video of a natural disaster and it's cold out and someone's house may have burned down or something like that, and if people are standing around outside, they give them these emergency blankets. So it's really shiny like that. It has that metal that's very reflective, and what they do with this is put it on like this, and then because that is very shiny, it is very reflective, what happens is the infrared energy that my body is radiating hits that shiny surface and then bounces back towards me. So it makes it very warm in here very quick. All right? So this does a pretty good job of warming you up if you have one of these emergency blankets like this. So this is extremely thin and it folds up into this like little thing about this big and about that thick. So good thing to have if you're camping or have in your car in case it breaks down. Now for some people, the emergency blanket isn't enough, so they can step it up a notch. And they might keep an emergency poncho with them. Yeah. So emergency poncho. Okay, same kind of rules apply here. The inside of the poncho is all silvery, so my body is radiating infrared energy. It hits the shiny surface and reflects that energy back to me, so it makes it nice and toasty inside this. I like this here because it has the hat, so it's going to keep my head warm. The energy my head is radiating is trapped and sent back, and I like how it has a little viewing point there so I can look out like that. But again, something that people a lot of times keep in their cars, or if they're camping, they help keep them warm when it's really cold conditions. All right, next up, absorbing. That's when the energy hits a surface and the surface just takes it in. The best absorbers are things that are dark and rough. So think about a blacktop driveway. When the sunlight hits a blacktop driveway, most of that energy gets absorbed and the blacktop driveway gets much higher temperature, it gets really hot. So the best absorbers are dark and rough. Like if you're shoveling a driveway of snow, usually you want to shovel down, if it's a blacktop driveway, you want to shovel down the blacktop. And the reason being is once the blacktop gets exposed, if the sun's out, that blacktop will absorb a lot of energy, and it'll heat up the ground around it and it'll melt a lot of the snow. If you just kind of like, skim over the top of it and leave like, about that much snow, your driveway's not going to clear out very easily because the snow is going to reflect a lot of the energy. If you can expose some of the blacktop, that'll absorb it and it'll make it a lot easier to clear out your driveway. All right, so that's absorbing. Another thing that can happen is, and you may notice this if you ever gone fishing or you use a pool skimmer or just stick a stick in the water, is when you put a stick in the water, it looks like it bends. It's really not bending. What's happening is the water is refracting the light that you use to see the stick. So refracting is when light or energy hits a surface and travels through it and then gets bent. Right? So again, you can notice it quite a bit with when you put a stick in water. I could do a little demonstration here to show you that now. So you can see where that little red dot is right now. If I put water between my laser gun and the board there, you're going to see the position of that red dot's going to change. See the red dot moved lower? There's where it's pointing to. When I put water between it, it bends down there. because the water is refracting or bending the laser beam. All right. So whenever the energy is going from one material to another, so if it was going from air to water, it would get refracted. If it was going from like clear glass to water, it would get refracted. If it was going from air to glass, it would get refracted. So if you're going through one kind of material and then you start going to another kind of material, that's when it gets refracted. All right, last thing to look at here is scattering. So scatter is when the energy hits the material and then bounces in a bunch of whole different directions. So the best example of that is probably on a cloudy day. All right, when there's no clouds, we get direct beams of light from the sun and you cast shadows and stuff. When it's cloudy outside, you don't really cast shadows. There's light there, but what's happening is the light hits a little water droplets, and so some of the energy bounces back up into space. Some of it might bounce sideways. It's not going to go in a straight line. It's going to bounce in a whole bunch of different directions. Right? That's scattering. A good place you can see that is when it's like really, really foggy outside and you're driving at night, or you're riding in a car at night. When a car is coming towards you, you don't see the head beams right away. You see like kind of like the fog kind of glow. That's because the light from the oncoming car, the headlights, are hitting the droplets of water in the fog, and it's kind of bouncing all over the place. And I can demonstrate that. Well, using the same beaker that I used a second ago, it's water with a little bit of soap in it. All right, so I just showed you that the water the light travels through the water, no problem. However, all right, if I try to have the beam of light travel through the so the bottom part where it's just the water, the beam of light travels through. If I have it go to where the foam is, the bubbles are, notice it's really not going through very well. What's happening is it's bouncing in a bunch of different directions in the bubble. So there it's just going through. There it's bouncing the bubbles in a bunch of different directions, and it's kind of lighting up the bubbles that are there. That would be an example of scattering. So it's hitting the material and bouncing in a bunch of different directions. All right. So that is what you need to know about electromagnetic energy.